Hey math fans, Alex here, coming to you today with chapter 6, a couple of limit theorems. Now this chapter is going to be a little bit more on the proof-centric side. The previous chapters, all you needed was multivariate calculus, but this is going to be a little bit more theoretical, but I'm going to try to supplement that with concrete examples. Okay, so let's go ahead and get started with section 6.1, the law of large numbers. So I don't love the book and the way they present the material in this chapter, so I looked at a couple of other sources to provide the information. And one of the questions that we should probably start to ask ourselves is that suppose we have a sequence of random variables x sub n, where n is allowed to roam in the natural numbers. Okay, so this is a sequence. This is a sequence of random variables and what do you do when you have a sequence of things? Well, you probably want to see if it converges to some limit. Okay, so the question that we're going to answer today is, what do we mean? What do we mean when we say that that sequence converges? This is not a dumb question at all. Okay, recall in Calc 2, so typically, we say that we can have a sequence of real numbers, or even complex numbers, depending on the class. A sequence of real numbers, we'll say maybe a sub n. And let's talk about what that means when we say that a sub n converges to some real number a. Okay, so this is a definition. Okay, so what does this mean? Well, informally speaking, it means that for some natural number n onwards, the terms in the sequence get really, really close to a. In fact, they get so close that the distance between an and a in absolute value is smaller than any possible number that I could pick. Okay, so typically we let that be epsilon and say that an minus a in absolute value is less than epsilon. For epsilon, some arbitrary positive real number. Okay, so let me just give you like a quick example, kind of the classic example. So let's go ahead and let an be the sequence 1 over n. Then, we all know that the limit as n approaches infinity of an is equal to 0. But we can prove that a little bit formally by saying that for some n onward, the distance between an and a is less than epsilon. Okay, so what you would do is you would just take an minus a, which is 1 over n minus 0, which we don't even need the absolute value anymore, and we have to show that 1 over n is less than epsilon. Okay, but this is actually just always true. So this is true by something called the Archimedean principle or property. And you don't have to know that for this class, but I'm just saying, just take my word for it. This is true. Take an analysis class if you want to learn more. But since this is true for any epsilon I can pick, there's always a natural number such that the reciprocal is smaller, which kind of makes sense. Let epsilon be some crazy number. I can always pick a natural number where 1 divided by that really big number is yet smaller than that. Okay? Okay, so hopefully that kind of makes a lot of sense from, real numbers, and if a sequence converges, you can even have a series converge, which we'll look at a little bit. So that was hopefully review now comes the tricky part, right? And the tricky part is random variables. So random variables are trickier. Why are they trickier? Well, they're trickier because xn isn't defined to be one value. Xn is a random variable, which means it can take on sometimes an infinite number of values. So Xn can take on many values, and in some cases, sometimes even in the case of a continuous random variable, could be uncountably many. Perhaps xn is someone's height. And obviously, someone's height's probably going to be somewhere between 4 and 7 feet, but there's a continuum in there. So it could be something like that. It could be scary. Okay, so this kind of begs the question, well, how do we make sense of the statement xn converges to n? So if I want to say something like the sequence of random variables converges to this random variable, what does that mean? Well, I'm going to go and tell you that I can break this up and say that this converges either in what's called improbability, or in distribution. Let me informally explain what that means before I give you the whopping definition. Note that although this can take on very many values, the probability of xn is a number. And we know that numbers can converge. Okay, so if I only look at the probability that xn takes on a specific value, maybe the probability that xn takes on maybe k. So the probability that x1 is equal to k, probability that x2 is equal to k, and so on and so forth, that forms a sequence of real numbers, because this is a single number, that is a single number, and then I form a sequence with those, and that could eventually converge to the probability that x takes on k. If that holds, we say that it converges in probability. If it converges in distribution, that means we look at specific traits of xn. Xn could be binomial or normal or uniform continuous. And we look at those particular character traits and we see if those slowly converge to another distribution. An example would be the binomial variables converging to a normal distribution. That was the de Moivre-Laplace theorem from the previous chapter. Okay, so I'm going to go and give you the definition right now. I'm going to write it and then we'll talk about it. Okay, so kind of a whopping definition, but it's important to go through. So I'm going to talk about 3 different ways that we can say xn converges to x. So it's a sequence of random variables. X is a random variable. The first way it could converge is it could converge in distribution, and that occurs if the limit as n approaches infinity of the probability that xn is less than or equal to some value x in the sample space is equal to the probability that the random variable x is less than or equal to little x in the sample space. Okay, the reason that this makes sense and the reason we say that this converges in distribution, this is the cumulative distribution function. This is the CDF. Okay, so this is the same thing as fn of x, and this is the CDF of this random variables. This is just f of x, right? So hopefully that kind of makes sense, right? The limit as n approaches infinity of all of these CDFs approach the CDF of just big X, okay? The second way is that xn could converge to x in probability, and that means if epsilon is allowed to be just some positive arbitrary real number, we have that the limit as n approaches infinity of the probability that xn minus x is less than epsilon is equal to 1. So what that's saying is if this is allowed to be any real number, as small as you could possibly think, I'm letting this be incredibly, incredibly small, well then xn is going to get closer and closer to x as n gets closer and closer to infinity. Okay, so the probability of this getting as close as I want as n goes to infinity, that's going to eventually equal 1. All right. Now that is very closely related but extremely different from this last kind of convergence, which is convergence almost surely. And we're still going to let epsilon be a positive arbitrary real number, but this time I have that the probability that the limit as n approaches infinity of the absolute value of xn minus x being less than epsilon is equal to 1. Okay, so a couple of things that I want to point out. I'm sure you have a lot of questions. First thing that I need to do is I need to give you some notation. Okay, so if xn converges to x in distribution, a lot of times we'll say this and put a d for distribution. If it converges in probability, typically we'll say this, but put a p. There are other notations, by the way, but this is just the one I'm going to try to use. And then almost surely, you would say a.s. Almost surely. Okay, so question 1, you might be wondering what the relationship between all of these different types of convergence would be. Okay, so we're going to go ahead and take the following as a fact. We're not going to prove that in this course, but convergence almost surely is the strongest kind of convergence, which is going to go ahead and imply convergence in probability, which then implies convergence in distribution. So that's the first thing. The second thing is you might be wondering what the difference is between convergence in probability and almost surely. Because if you look at the criterion, they look almost identical, right? In fact, they are almost identical. It's just that the limit operator and the probability are flip-flopped. So how can that make something so different where one implies the other, but not the other way around? Well, I'm going to give you an example that will hopefully clear things up. All right, so let's go ahead and do that to finish off this video. All right, so here's our example. We're going to go ahead and let omega be some sort of event where we draw a random number between 0 and 1. So it has the uniform continuous distribution on 0 to 1. We just pick a random number and fix that value. Okay. We're also going to define something called the indicator function. Don't know if you've encountered this in other classes, but the indicator function over an interval a to b of omega, if you plug in omega, omega is clearly either going to be in the interval, in which case just go ahead and let the indicator be 1, or it's not in the interval and let it be 0. So it basically says, is omega actually in your interval? Okay, so remember we're trying to differentiate between converging in probability and converging almost surely. So we need a sequence of random variables, and I've kind of concocted a very special sequence of random variables. So x1 of omega, whatever omega is, it could be 0.7 or 0.5 or whatever, it's fixed. We're just going to let it be omega plus the indicator function on 0 to 1. Okay? So it's either going to be in 0 to 1 or it's not. Well, clearly it is going to be between 0 and 1 because omega was defined to be somewhere between 0 and 1. Okay, so perhaps maybe this is my omega right here. Okay, so this would take on the value 1. Okay. Next, x2 of omega is going to be omega plus the indicator over 0 to 1/2. Okay, so if this is where my omega is, you can imagine that I'm going to chop the interval between 0 and 1 like this, and now I have 2 regions, and omega can only be in one of those regions. I guess it could technically be exactly at this point right here, and then you just get lucky, but most of the time that's not going to happen. Okay, so this is going to be the interval from 0 to 1/2, and this is going to be the interval from 1/2 to 1. This time omega is clearly only going to be in one of these, so in this case the indicator function here would be 0, and here would be 1. Okay. Next, we're going to split it up into 3 regions, right? Here, here, and here. And again, omega is probably only going to be in one of those regions. Okay, so out of these three intervals, omega is probably only going to be in 1 out of 3 of them. And then the next 4 random variables, you would chop it up into 4 intervals and so on and so forth. So the values for which the indicator function is 1 are getting more and more sparse, is what you should take away from that. Okay? So that is xn of omega, where the random variable x of omega, we're just going to define that to be omega. Okay? So we need a value for omega to play around with, so maybe suppose omega is equal to, I don't know, 0.6. Okay, then xn of omega is going to equal omega plus some indicator function. And I don't really, feel like putting that in there. Which means that xn of omega is either going to be what or what? Well, if the indicator function is 0, that means that it's either going to be 0.6 if the indicator function is 0, or 1 plus 0.6, the indicator function is 1. Okay, and that of course depends on the value of this indicator function. Okay, so now comes the convergence stuff. So as n goes to infinity, the interval 0 to 1, remember, we're going to split it off into more and more regions, and the indicator function is only going to be 1 for one of those regions, or maybe even a couple, but if you, put it in more and more regions as n goes to infinity, it means it gets way less likely, okay? So as n goes to infinity, we can say 0 to 1 is more finely partitioned. Okay, so omega is, omega, I should say, the indicator function over some region equaling 1 is less likely. Okay, so for some epsilon positive arbitrary, let's look at it. Okay, so we have that. I'm going to claim that the limit as n approaches infinity, this time the limit is on the outside, of the probability that xn of omega minus x of omega is less than epsilon. I'm going to go ahead and claim that that's equal to 1. Why? Well, this is for sure 0.6. This is either going to be 0.6 or 1.6, where this is more likely as n goes to infinity. So basically, for some n onward, I can guarantee that this will occur infinitely many times. Okay, so what we can say is that I'm taking 0.6 minus 0.6, which is 0. Epsilon is clearly always going to be bigger than 0, so it really doesn't matter what epsilon is. So xn converges to x in probability. However, let's take a look at the probability of the limit as n approaches infinity of xn of omega minus x of omega being less than epsilon equaling 1. So the probability of this equals 1. Is that true or false? We should always be skeptical anytime someone says the probability of an event is 1. That means this must happen every time. Is that true? No, it's not. The indicator function gets less likely, but it still has some sort of wiggle room to occur. Okay, so again, this was still our 0.6. This is still 0.6 or 1.6, where this could happen. This could happen. And in fact, it does happen with non-zero probability. Doesn't matter how big your n is. It doesn't matter how small your epsilon is. Eventually, you're going to run into a situation where the indicator function is 1, in which case this happens. So whatever epsilon you pick, it's not going to hold for all of them. Okay, so the probability of this occurring can't be 1, so this statement is false. So this is false since xn omega equals 1.6 for some n. Doesn't matter how big, but whatever your threshold is, I can find you an n that the indicator function will eventually turn on for. Okay, so in this case, we say that this doesn't happen. This does not happen. Okay, so that's kind of the difference. It's a very subtle difference, and you might be wondering at all, why am I even talking to you about these things? Okay, so last thing that I'll leave you with, why is this important? Well, in this chapter, and here's my overview of the chapter, we're going to be talking about 3 main theorems, okay? The first thing that we're going to talk about is something called the weak law of large numbers. I'm just going to abbreviate. Then we're going to talk about its counterpart. We're not going to spend too much time on this, but the strong law of large numbers. And then the star of the show, the central limit theorem. These are all limit theorems. These are the 3 most important ones that we're going to study. And the reason that I spent today talking to you about what convergence means in probability is because this converges in probability. This converges almost surely. And we're going to see that this converges in distribution. So we'll start taking a look at that in the next video. Thanks so much for watching, and I hope you have a great rest of your day.